Hello everyone. Welcome back to the course on time and space complexity analysis. I am Sanket Singh, and in this lecture we are going to continue our discussion on problem solving around calculation of worst case complexity of different algorithms. In this playlist we have already completed that why efficiency of algorithm is important, how do you measure the algorithm with respect to hardware, and how a single CPU core system works. We already talked about rate of growth and asymptotic analysis. And even in the last lecture, I already talked about a few problems and how you can calculate the big O notation based worst case complexity for them. In this lecture also, we are going to solve around 3-4 more questions, which are going to give you better clarity that when you actually see an algorithm, how you should move forward to calculate the complexity for it. In my opinion, understanding how complexity of algorithm is calculated gets more clear when you solve more questions or you see more algorithms and try to calculate complexity for them. It's not a one time process. You need to be iterative in that. And this playlist is going to focus on that. We are going to solve a lot of questions where we will be calculating the time complexity of different algorithms. This lecture is going to be part of a bigger playlist that we are building for time and space complexity analysis to make sure that you guys get a good grip on this particular topic. So, without any further delay, let's just start and let's start solving our first question. Now we have talked a lot about the worst case analysis, but sometimes in some algorithms, we also need to take a look at the best case analysis, because sometimes what happens is, let's say there are two algorithms, algorithm A1, algorithm A2. The worst case of both the algorithm is same, but then we have to decide still which is the better algorithm. Then we try to decide them based on their average case and the best case, because if the worst case is same, we try to look at the average case, we try to look at the best case, right? So there are algorithms, for example, like bubble sort. You will read about bubble sort when you will move ahead in your programming part, right? And there is one more algorithm like selection sort, right? Now both of these algorithms have got their worst case complexity as order of n square, but still we have to decide which one of them is better. So there are other criterias. One of the criteria is which one is having a better best case. So bubble sort has a better best case. In the best case, it works in omega of n, right? So it's important to understand the best case analysis also, whereas selection sort works in omega of n square only. So we'll talk about this omega notation and we'll talk about the best case analysis. Best case analysis. We are technically talking about big omega notation, right? What is the best case analysis and what is this omega notation, right? So if I talk in terms of mathematical notation, so we can say that, let me draw a graph, or let me just quickly get a graph for you guys. So what we can say here is that if you take a look at this graph, so we can say the big omega notation, the big omega notation gives the tight lower bound, of the given algorithm, right? So we say that, let's say if we have a function f of n, right? Then we can say that for n greater than n naught, f of n will be greater than or equal to cg of n, which will be greater than or equal to 0. What does this inequality denotes? This inequality denotes that if f of 1, what is the least value that f of 1 can go to? F of 1 can never go lesser than cg of n. That is, if f of 1 works in the best possible way, then what's the best case there, right? If it has to work in the best way, what's the best possible case? That f of n will never go lesser than this. This is the least value that f of n can go to. So we have to approximate the least value that f of n can go to. And that particular function g of n, we call it as omega of g of n. We call it as the best case of f of n. We call it as the best case of f of n, that if your function f of n has to work in the best possible way, in some cases only, if your function has to perform the best, this g of n is going to be the best approximation for that. It is never going to go lesser than cg of n. It will be always at least cg of n or greater than cg of n. You can see this here, right? That this inequality denotes that f of n is at least cg of n or greater than c of g of n. It can never do better than cg of n. That's the best case analysis. Right? So if I take an example, in front of you, right? Let's say f of n is equals to 5n square, right? And we have to calculate the big omega for this. Then we can say that c is equals to 5, for c is equals to 5, and g of n is equals to n square. We can say it is equal to big omega of n square for all n naught equals to 1. The value of n naught will be equals to 1. That is, this function 5n square is going to perform the best that it can perform is going to be 5n square. Otherwise, it will always perform worse than 5n square. It will never perform lesser than 5n square, right? So if you see it in terms of complexity, in terms of some coding implementation, so let's say if I write a function, let me remove it. Let's say if I write a function f of n, right? And then let's say we say that we have an array, right? And inside this array ARR, I have to search for this element n. So what will I do? I'll just loop over the array. Don't worry. Again, as I said, this is all language agnostic. So what I'm doing is I'm looping till the length of the array. And we say that if ARR at I equals to n, we return I. Otherwise, we return, let's say, -1. So if you carefully see, what I'm trying to do, I'm trying to search for the element n inside the array. Now, what will be the best case? The best case is going to be that the element is present on the 0th index only. Let's say this is the array. And there was 3, 4, -1, 2, 5, 6. And the value of n was equals to 3. So 3 is present at the 0th index only, right? So your for loop will run. And on the 0th index only, you will detect the element and you will return it. Can I say that? In that case, you will just do one iteration and boom, you are done. You don't need to go to the remaining elements. So we can say that the best case of this function, is going to be what? Omega of n. But what will be the worst case? Worst case, you can say that maybe let's say n is equals to 30. That is, it is not even present in the array. If it is not even present in the array, you will read all the elements, all the n elements. You will like let's say there are total x elements. All the x elements you will read, right? Let me give better notation. Let's make it as element. Okay, let's make it as element and let's keep n as the length of the array. So let's remove this. I wrote it by mistake. So what I'm saying is, in the best case, maybe there can be a case that at I is equals to 0, you found the element. So you will do constant operation. Whereas in the worst case, what can happen? The element is not even present in the array. So you will read all the n indexes, right? That means in the worst case, you are going to do order of n. But in the best case, you will do omega of 1. Whenever there is a constant number of operations, no, see, if we found it at the 0th index only, so you just do constant operation. Whenever we overall do constant operation, now constant operation can be 1 operation, 2 operation, let's say 15 operations only. We are never going to go beyond 15 operation. We just represent it by 1. So even in the worst case, if the worst case is constant, so we say O of 1. The best case is constant, so we say omega of 1. So here it will be omega of 1. So omega technically denotes that if the algorithm is going to perform good, how good, like what's the best case for it? What's the tightest lower bound? It can never go beyond this. It can never go lesser than this. That is our case, right? That's what best case analysis works on. But majorly when we are doing algorithmic coding, when we are developing softwares, we generally care more about the worst case, because worst case generally occurs with a much worse complexity, taking much more time, and that's what we have to optimize also. So we are majorly concerned about the worst case analysis. Now we have one more complexity case, that is average case. Now when we say average, then it's not the worst possible case that can occur. It's not the best possible case that can occur. It's like an average that, let's say, you run it for 100 different samples or 100 different type of input. On an average, how does it perform? On an average, like, you're not just considering one case where it was performing extremely good. You're not just considering one case where it is performing extremely bad, but instead you take an overall average of multiple operations. Let's say, let's just take a case. Let's say some algorithm is taking, sometime it just take one iteration for some cases, but for some cases it takes n iteration. For some cases it takes n by 2 iterations, and so on. So what do? You just sum up all the iterations and divide it by total number of operations that you actually did, which will help you to get an average number of operations that happens, or average number of instruction that goes on per operation, right? That's what average case is. In average, we just take a look at overall average picture of the algorithm, that we consider that some of the cases will be very good, some of the cases will be extremely worse, some of the cases will go on average. How does it perform? So there are special algorithms. For example, quicksort. There is an algorithm called as quicksort. Quicksort relies a lot on the average case complexity, because the worst case of quicksort is very bad, but that worst case now occurs with a probability of, like, the probability of the occurrence of the worst case of quicksort is very less. Like, you can say that it will never even occur. Sometimes the probability is so less that the worst case of quicksort doesn't make it a very bad option. We'll learn about, we like later when you will learn more about around algorithmic analysis, we'll learn about quicksort. But the thing is, the main thing about quicksort's complexity is that the worst case of quicksort occurs very less number of time. The probability of occurring of quicksort's worst case is very less. That's why we choose quicksort, because of the average case, because on an average quicksort performs very good, right? Similar thing exists with addition of new elements in arrays. If you have to add new elements in the array, there is a very efficient way. I'll talk about it. That efficient way sometimes perform very bad, sometimes it perform very good. So we are not able to analyze. That's why we rely a lot on the average case analysis, right? So that's what big theta is. Big theta works on an average, that overall how does the performance of the algorithm looks like. But still we are more concerned about the worst case rather than average or best case, because even if the worst case hits once, it's still very bad. So majority of the analysis that we are going to do is going to be around the big O notation.